yellow sheet. We're going to add to that today because there's going to be more formulas today. All right, so the group quiz. So we are not doing a quiz while we're on Zoom. So we decided to go ahead and we're going to do lesson 4.2 today. And then the quiz is now going to be Friday for you guys and then Monday for the other group, the other two groups. And then, but everything else is going to be on track where we are still going to have the test on next Friday. So you guys are going to have like a quiz on a Friday and then a test the following Friday. Lucky you. Okay. I'm going to submit my attendance. I still haven't seen Maya or Keston. Okay. All right. So here we go. Today's the day you've all been waiting for. We're doing antiderivatives. So we're taking a little break from area under curves, and we'll get back to that in the lesson next week after the quiz. But for now, we're going to be talking about anti-differentiation. And as you can imagine, that means the reverse process of differentiation. So we're basically working backwards. So let's see, this is going to be a little bit weird. I'm going to ask for a little bit of feedback here verbally, not on the chat. This is probably the only time I'm going to do this right now. But if anybody want to take a guess on what the like if the derivative was 2, so f prime of t is equal to 2, what would f of t be?
2x.
2t.
Yeah, I heard somebody say 2x and somebody said 2t. It is 2t. 2x would also be sort of the instinct there. But the variable, independent variable, it was bt, so it is 2t. Okay, what about the, and Marcus, I'm sure you've already learned this on TikTok, but if the derivative was 2x, what would the original function have been for the antiderivative?
X squared.
X squared, good, x squared. And then if the derivative was 3u squared, what is the antiderivative, or what would the original function have been? 3u squared. Did I say 3u squared? Say again.
U cubed.
U cubed. That's right. U cubed. And then if the derivative was x squared, what was the original function? This is a little challenging.
1/3 x to the 1/3 x cubed.
Yes, Ben, 1/3 x cubed. Okay. So we're going to get into how to figure that out without sort of having to think backwards. Keston thought it was lunch. Oh, there he is. He's in the waiting room now. Oh, Keston. Okay, so the thing is when we say that the antiderivative is 1/3 x cubed or u cubed, this is not exactly true, because the truth is that if I had 1/3 x cubed plus 2, the derivative with that would be x squared. If I had 1/3 x cubed plus 100, the derivative of that would also be x squared. If I had the 1/3 x cubed minus 7, the derivative of that would also be x squared. So we're actually going to use a letter that's called the constant of integration. So we say that the antiderivative would be 1/3 x cubed plus c, where we call this the antiderivative. Can't spell, hold on. The antiderivative or the integral of x squared. And c is known as your constant of integration. So antiderivative and integral tend to be used kind of interchangeably, like they're synonyms, although technically there is a slight difference between the two, but often I will just use those terms interchangeably, so you can as well. Okay. And if anytime, remember these notes will be up on online later. So let's talk a little bit about notation. If the function is called f prime and you're trying to find the antiderivative, we can call the antiderivative of that just f of x, which seems logical because with derivatives, we've been moving forward and now we're moving backward. And if the function is called g prime of x and we want the antiderivative, we can of course call that g of x. All seems very logical. But the challenge is, well, what if the function is called f of x and we're trying to move backwards to find the antiderivative? So what we do is we use a capital F of x. So if your original function is lowercase f of x, then your antiderivative would be capital F of x. And you might wonder, well, what if the original function was called capital F of x? What would its antiderivative be called? Well, usually you're not going to see that. And second of all, I guess you could do like a bubble letter F of x. You know? I mean, you don't actually see that, but you could say that. Okay. So this notation, we've seen this already. This is this little elongated looking s. This is your integral sign. And so this is how we can write it. We can say the integral of f prime of x dx. Remember, anytime you write an integral sign, you need to put this dx here. That would be equal to f of x plus c. Or if you had the integral of f of x dx, then you would write that equal to capital F of x plus c. So this is read, this one up here is read as the integral of f of x with respect to x. That's how we would read the dx. And you would say equals capital F of x plus c. Okay, so a little a bit more about notation. So as I said already, this little elongated S looking symbol is called the integral sign. The integral sign. Whoops. And then this business here, the 3x squared, that is called your integrand. You don't really need to know that, but it's there. And then the dx part, that's called your differential. And one of the reasons why it's helpful to have the differential is because it tells you what your independent variable is. So when we had that one example before where I said that f prime of x was equal to, or f prime of x or f prime of t was equal to 2, and we said, well, then f of x would have to equal 2t, or sorry, f of t would be 2t. But if you had something like the integral of just 2 dt, then you know the answer is going to be 2t and not 2x. So the differential there helps you to identify where your independent variable is. And then the x cubed plus c, that of course is your antiderivative. Still can't spell, good Lord. And then the plus c, as we said already, is called your constant of integration. And we just use c because the word constant starts with c. Okay. I'm going to skip ahead because I had a lot of slides for this. All right, so here's where we're going to talk about the pattern. Some of you might already know the pattern. Is that a hand raise? Oh, yeah, Elsie, go ahead.
Are the terms antiderivative and integral interchangeable? Like, can you use them as the same thing?
They are slightly different, but yeah, you can use them
Okay,
interchangeably.
thanks.
Mhm. All right. So the if the function was 2x, I think we did this one earlier, then the antiderivative of that would be x squared. And for 3x squared, the antiderivative of that would be x cubed, sorry, x squared plus c, x cubed plus c. So you can check it by, of course, doing the derivative, right? When the derivative, you take the 3 down to the front, you subtract 1 from the x squared, and you would get the 3x squared. And same thing here. Take the 2 down to the front, subtract 1, so you just get 2x. But then it gets a little bit more challenging when it's not sort of instinctual. So the process here is that you're going to add 1 to your exponent. If we were together in the room, I would make you come up with a pattern, but it's a bit awkward with the Zoom, so I'm just going to tell you. You're going to add 1 to that exponent and then divide by that new exponent. So in this case, it's going to be x cubed divided by 3 plus c. There was a pop-up. Did somebody have another? I saw something. So if you can check that with this one up here, right? If you did the 2x, you can say that's going to be 2x. Let me write it in green. 2x squared divided by 2 plus c. And of course, the 2's reduced down to just give you the x squared. Same thing for the next one. You could have called that 3x cubed divided by 3. So you're adding 1 to the exponent, and you're dividing by that new exponent. So try, I'll give you maybe 15 seconds to try the next one. So x to the 4th, x to the 10th, x to the 76th, and x to the 1/3. Okay, so for the next one, you should have gotten so purple, x to the 5th divided by 5 plus c. This one would be x to the 11th divided by 11 plus c. I should also point out that you could have called that 1/11th times x to the 11th plus c. It's the same thing. Then the next one is x to the 77th power divided by 77 plus c. And the next one, we're going to add 1 to the exponent. So 1/3 plus 1 is going to be 4/3, x to the 4/3 divided by 4/3 plus c. But we're not going to leave it like that because dividing by, we don't want to have a complex fraction. So dividing by 4/3 is the same as multiplying by 3/4. So let's call that 3/4 times x to the 4/3 plus c. And we'll leave it like that.
Miss
Any
Oak,
questions?
can you
Yeah, go
explain
ahead, Corey.
the pattern again?
Say again.
Can you explain the pattern again?
Sure. We're about to write it down. But you're adding 1 to the exponent. So you had the exponent of 10. So you're adding 1 to that exponent, and then you're dividing by the new exponent. Add 1 to the exponent, divide by the new exponent. All right, so this is where we're going to talk about some integration rules. There are a lot of integration rules, more than the differentiation rules. And we're going to write down some of them today. So this is where, if you have your yellow sheet, I would recommend that you flip it over on the back of your yellow sheet. So like the front of your yellow sheet is like differentiation stuff, and then the back will be your integration stuff. So today we're going to have these 5, and then we're going to do a couple of examples, and then we're going to have 5 more after these. So the first one is, well, actually, let's jump down to this one with the x to the n. So this is where what we were just doing. We're going to add 1 to the exponent. So x to the n plus 1, divide by the new exponent, n plus 1, and then plus c. Now there is a condition on this one, which is that n cannot be equal to -1. And we'll talk later about what happens if n is equal to -1. Okay, the rule right above it with the integral of k dx, this is a constant, and they're using k to represent constant, so it's not to be confused with our constant of c. And it's going to, essentially, you can think about this as being like k times x to the 0. So then you can follow the same rule. This rule, by the way, is called the power. Whoa. It's called the power rule. So you see, it's like the opposite of the power rule for differentiation. So if you think about this one, you have k times x to the 0. So add 1 to the exponent, which is going to be 1, and then divide by the new exponent, which is going to be 1. So that's just going to give you kx plus c. Okay, then we have the antiderivative of cosine of x. If we were together in the room, I'd see if you guys can guess it. But it is the sine of x plus c. Technically, the parentheses go around that x there. Then the antiderivative of sine of x is going to be negative cosine of x plus c. So this is going to get messed up in your brain because you're so used to saying the derivative of sine is cosine and the derivative of cosine is negative sine, but now we're going backwards. So you have to think, okay, well, the antiderivative of cosine is going to be sine and the antiderivative of sine is going to be negative cosine. So it's going to be, take some thought there. All right, and then the next one is tangent, because the derivative of tangent is secant squared. All right, we're going to do some more examples, then we'll come back and do more rules. So here are the first two examples. I will be quiet while you try these. Feel free to pop in with a question if you have one. Okay, so for number one, we're just going to go term by term. So the antiderivative of 5x to the 10th will be 5x to the 11th divided by 11. Then a minus sign. Antiderivative of secant squared is tangent of x. And the antiderivative of 4 is 4x plus c. And that's it. That's all you have to write. For the next one, I probably should have given you a tip that you needed to distribute that x squared first. This is a product of two different functions, and there is no such product rule for integration. So we're going to clean it up as much as we can before we apply our differentiation or integration rules. So I'm going to call this then the integral of x cubed minus 4x squared dx. So I have to distribute that first. And then I can apply, in this case, we're using the power rule of integration. So that's going to be x to the 4th over 4 minus 4x cubed over 3 plus c. Okay, I'm going to go on to the next slide. So try these. I will tell you, I'm going to write down a little tip here. So for this one, you need to split the fraction first. And then for this one, you need to expand it first. If you don't know what I mean by split the fraction, then do number 4 first, and then I'll talk about what split the fraction means. Okay, when I say split the fraction, what I mean is to call this the integral of x over the square root of x plus 1 over the square root of x dx. I'm going to go ahead and work through number 3. So we have x over the square root of x, and remember this really means x to the 1/2 down there in the denominator. So if you are dividing your bases, actually, let me go ahead and rewrite that so you can see what I'm talking about. X to the 1/2, x to the 1/2. So when you have x to the first over x to the 1/2, you're dividing the bases, so you need to subtract your exponents. So that's going to be x to the negative 1/2. I'm sorry, positive 1/2. I would say negative. I think I'm thinking of the next term. And then that would be x to the negative 1/2 dx. Okay, because this is in the denominator, so I put it up in the numerator to make that exponent negative. And now you can do the power rule. So you're going to add 1 to the exponent. So 1/2 plus 1 is going to be 3/2. Divide by the new exponent, 3/2. Plus negative 1/2 plus 1 is going to be positive 1/2. Divide by the new exponent, which is 1/2, plus c. I don't want to leave it like this because this is a complex fraction. So in the next step, I'm going to call that 2/3 times x to the 3/2 plus 2 times x to the 1/2 plus c. And if you want, you can turn that back into radicals. So you can call that like the square root of x cubed and the square root of x, but you can leave it with rational exponents. Okay, so for the example 4, the expand first means I'm going to essentially write that twice and then FOIL it. So 2t squared plus 3 times t squared plus 3. So that's going to be the integral of t to the 4th plus 6t squared plus 9 dt. And if you want, you can put parentheses around your integrand. And then do the power rule. T to the 5th over 5 plus 6t cubed over 3 plus 9t. Not to be confused with 90. 9t, 90 plus c. And then, of course, you can clean up the 6 over 3. Call that t to the 5th over 5. Or if you can call that 1/5 times t to the 5th if you like. Plus 2t cubed plus 9t plus c. Any questions so far?
Do you always want us to simplify it, or if we left it as 6t cubed over 3, that's okay?
It probably wouldn't penalize you if you left it as 6t cubed over 3, but it usually makes your work easier later if you simplify.
Okay.
All right, let's go back and write down 5 more integration rules, and then we have a total of 7 examples. So we'll go into example 5. All right, so these are 5 more integration rules. So let's, I'll give you a chance to copy these down, and maybe you can figure out what these are. And that one, oh, maybe that one's a little tricky. I'm gonna be quiet for about a minute, so you can write this down and maybe fill it out if you can figure it out. All right, for the first one, we've got secant tangent. So the antiderivative of that is secant. Secant of x plus c. Cosecant squared, the antiderivative of that will be negative cotangent of x plus c. Remember, the derivative of cotangent was negative cosecant squared, so the antiderivative of cosecant squared would be negative cotangent. And for the next one, cosecant cotangent, the antiderivative would be negative cosecant of x. The next one, e to the x, that's the best one, is just e to the x plus c. And then the next one is the natural log of the absolute value of x plus c. Now, the absolute value technically is required. I wouldn't stress out about it too much because it's really just a safeguard to ensure that your function is positive, because a natural log function is always positive. So you can't have, the input of a log function is either 0 or no, it has to be bigger than 0. So just to safeguard that you can't put a negative value into a log function. Okay. This example, a little bit different. We've got the integral or the antiderivative of sine of x over cosine squared. I'm going to give you a chance to copy it down if you're taking your own notes, and then I'll walk you through it. Okay, so I have a quotient here. And like I said before with the product rule, there's no product rule or quotient rule for integration. It's only for differentiation. So you need to sometimes manipulate your original expression so that you can use the rules that we know, those 10 rules that we just wrote down. So what I'm going to do is I'm going to split this up a little bit and call this will remind you of pre-calculus from last year when you had to do some verifying and simplifying of trig identities. So I'm going to call this integral of sine of x over cosine of x times 1 over cosine of x. This is sort of another way to sort of split your fraction, if you will. And hopefully you agree that these are the same thing, because with fractions, you just multiply across the top and across the bottom. So then let's simplify. What is sine over, I don't know why I'm asking because you guys are all muted, but the sine over cosine, that's tangent. So that will be tangent of x. And then 1 over cosine of x is secant of x. And then you can look back at your rules and see that the antiderivative of tangent times secant is secant plus c. Okay, couple of properties. I want to get through these little kind of quick because we have 10, 15 minutes left, 35, 15 minutes left. So this property just says, it's called the constant multiple property, and it says that if you have a constant in front of your function, then you are allowed to take that constant outside of your integral and do k times integral of f of x dx. And then the sum difference property says that you can do the integral of the sum is the sum of the integrals, or the integral of the difference is the difference of the integrals. We have the same rule for differentiation. So we actually already put these rules in practice when we did, well, really any of these examples. So when we got the t to the 4th plus 6t squared plus 9, the difference of the sum of the integrals is integral, the sum, that is what allows us to just add the different terms. And also the fact that you've got this 6 in front of the t squared, you technically could take the 6, if you split it up into different integrals, then you can take the 6 on the outside. So most of the time, the properties are sort of embedded into what you're doing, but there will be other times in the future when, in particular, the property about the constants will be very useful. Okay. And then I've already mentioned Achtung, this is German for caution. I've already mentioned that there's no such thing as a product rule for integrals, and there's no such thing as a quotient rule. It's one of the reasons why integrals are harder. All right, so this, and then we're going to talk about this, and we'll do the last 2 examples. So it says that when we do this, this is your whole general solution. It's like your whole family of antiderivatives. And it means like if you have you can have a parabola, right? So it's 1/2 x squared plus c. So this green parabola could be could have been the original function or the antiderivative, or it could be the blue one, or it could be the red one, or it could be the purple one. So if you only want the blue curve, then you're going to need to be given, sometimes you're given specific information about the function, that you know the function passes through a particular point, and that's called the particular solution. So we're going to actually be able to figure out what C is for a very specific or a particular case. So our last 2 examples are about that. Okay, so the function says big F prime, so capital F prime of x is 1 over x squared, where x is positive. We want to find the particular solution given that the initial condition f of 1 is equal to 0. So if you don't have the notes printed in front of you, I'll give you about 30 seconds to write this down. Okay, so you're given the derivative, and we are going backwards to find the original function, and we know that on the original function, it passes to this point 1, 0. So we're going to do the antiderivative. So I'm going to write down the integral of 1 over x squared dx. That's going to give me capital F of x. You might be tempted to go ahead and add 1 to the exponent, divide by the new exponent, but you can't do that when it's in the denominator. The power rule doesn't apply. It's the same thing with differentiation. We need to get that x up into the numerator. So we will have x to the negative 2 dx. And now add 1 to your exponent. So negative 2 plus 1 is negative 1. Divide by the new exponent plus c. I'm going to clean that up a bit. I'm going to put the x to the negative 1 down in the denominator, and then the negative sign, I'll just put it up in the numerator. So it's going to look like this. And now we're going to find that c value. We're going to substitute the 1, 0. So we have negative 1 over 1 plus c is equal to, I said 1, but I wrote x. Negative 1 over 1 plus c is equal to 0. So c equals 1. So f of x, capital F of x, is going to be negative 1 over x plus 1. Let me go on to the next example so that we can finish it. And then if you want me to go back afterwards, you can. You can ask. I will. All right. The last example, this will take us back to our straight line motion lesson. So we have a of t. This is our acceleration function. is 12t squared minus 6t, not to be confused with 60. 6t, 60. The initial velocity, it's 5 feet per second. The initial position is negative 15 feet. We want to find the position function s of t. We need to go backwards twice. We have the acceleration function. We're going to have to go backwards and find the velocity function. Then we're going to take the velocity function and go backwards and find the position function. So the acceleration function, or sorry, the velocity function will be the integral of the acceleration function, a of t dt. So in other words, it's the integral of 12t squared minus 6t dt. This polynomial, so we can just use the power rule. So 12t cubed over 3 plus 6t squared over 2 plus c. Clean that up a little bit. 4t cubed plus 3t squared plus c. We need to find that c value for our velocity function before we can attempt to find the position function. So we're going to use this information here. It says the initial velocity is 4 feet per second. So we're going to say that's when t is equal to 0 for your initial velocity. So 0, 5 is what we have on our velocity function. Substitute 0, 5. You could do this in your head, absolutely. It's pretty simple because you're working with 0. So we're going to have 5 equals 4 times 0 cubed plus 3 times 0 squared plus c. You can pretty much easily see that 5 is going to be c. So that makes your velocity function equal to 4t cubed plus 3t squared plus 5. So now I can go find the position function, which is going to be the integral of the velocity function. Use the power rule again. And then we will substitute our initial position information. So the initial position is negative 15. We're going to substitute that. To find C. And again, you can do this in your head. It's not that difficult. So our final answer is t to the 4th plus t cubed plus 5t minus 15. All right, your homework is a circuit worksheet. If you don't have a printer, you'll just have to do it. What am I trying to say? On a piece of paper. And but it's not going to be due tomorrow. We meet tomorrow, but you're going to have your group quiz tomorrow. So the due date for this homework is not going to be until Tuesday. So when I see you tomorrow in person, I will give you a paper copy of the circuit if you want it or not. So if you don't have any questions for me, you can go ahead and sign off.